We are learning about the transfer function. So the transfer function is the output or input of a linear time invariant system, a system which does not change its response with the passage of time. So what happens? This is the transfer function definition of a linear time invariant differential equation. Is defined as the ratio of the Laplace transform of the output, which is the response function, to the Laplace transform of the input driving function, under the assumption that all initial conditions are 0. So this is the formula for that. And then Laplace transform of output over the Laplace transform of the inputs at 0 initial conditions. This is known as the transfer function. And we can represent a transfer function in a block diagram, which I'm going to go over just in a bit. So let's listen to some of the properties of transfer function. But why do we need a transfer function? So let's see. The first point is the transfer function of a system is a mathematical model of that system, in that it is an operational method of expressing the differential equation that relates the output variable to the input variable. Second point is the transfer function is a property of a system itself, unrelated to the magnitude and nature of the input and or the driving function. So in this case, we don't know what is the input magnitude or the driving function. And the third point is the transfer function includes the units necessary to relate the input to the output. So you can read it and so on. The fourth point, transfer function of system is known. The output or response can be studied for various input and so on. And this is an example which is about which is similar to our lab 2 part B, where we had the damper. So this is the transfer function comes from the differential equation of motions, and once you know the differential equation of motion, then you can find the output. This is output over input. This ratio, this is the transfer function. And we had, in our case, if you go back to our lab 2 part B, so we had some mass dampers. So let me copy and paste here in our lab 6. So let me go over here. So if you take a look, this is a mass spring damper system. So we know that the spring constant is 800 or 400 or 200, depending upon which spring you have attached, and you have a damper. So we can find out the damping coefficient. Some people write down B as a damping coefficient, some people write down C. It does not matter. So but the thing which matters is you should know how to derive the equation of motion, and then from there how to find out the transfer function. Transfer function gives us the time response of any driving input. It could be an impulse input, it could be a step input, it could be a sinusoidal input, and so on. This is the algorithm which I have written, copied and pasted from the Ogata book. So what I'm trying to show you here, yes, this is the algorithm that first of all you will find out. This is about the impulse response function, and the impulse response is like a hammer. You just hit this this system. In this case, this is our carriage. If you hit it with a hammer or like a tap, it you just change the initial condition and automatically it starts vibrating. And we have to understand what is the output over input. This is y is our output and input is our x. So if you know this transfer function, then you can find out the y of t, and y of t is the output response, and response in time domain. So if I go back and pull this up from the previous lab, so the time response, so that you should be able to see, and this is the time response of so okay, so imagine this is the time response. This is a time response of a step input. As you can see, the mass is displaced. Look at here, this mass has been displaced from 0 to a new position. I think this is 0, this is negative, so it's from negative to 0, so it has gone up to the next level, so it's a step response. But you see, this is the these are the peaks, and you can find out the natural frequency of this system. So this is how what the transfer function is. In this lab, I'll assign you some of the plants, and some of the questions I'll assign you, and how to find out the transfer function. From there, this would be given in that exercise. And this is another example of the block diagram. You have to draw a block to represent a transfer function. On the right hand side, this is the output. On the left hand side, this is the input, and output in our case is displacement of this mass. Input in our case is the driving force. It could be as I mentioned, in this case this is a step value, but if you see what is the time response of an impulse, for example, the mass is hit by a certain force, goes up, comes down. If it is a second order system, it suddenly goes up, comes down, and then it becomes at 0. This is our displacement of this mass. This is our time. Actually, the impulse is so fast that there is no lag. So I should redraw it such that it should be very parallel to the y-axis, and then this is nicely drawn. This is our time response of this mass spring damper system. And the impulse in our the control theory class, which we have learned different types of driving input. Impulse is represented by this delta function, and the Laplace transform of an impulse is 1. And similarly, you should remember these Laplace transform of a unit step is 1 by s, and Laplace transform of a sine signal is 1 over s square plus 1, or if it is omega t, it is omega squared. And Laplace transform of 1 over s plus a, which is a transient response, it is equal to minus e to the negative at. And Laplace transform of t is 1 over s squared, and so on. These are important because our transfer function is in the Laplace transform. So you have to take first of all, you derive the equation of motion. This is the differential equation of motion, second order, and then after that you take the Laplace transform. And I can explain this in a more elaborate way. For example, this is my so let's do this problem a little bit in more detail. So I would just show you. So this is I'm sorry, this is so the equation of motion comes from the free body diagram. So this is our coordinate of this mass, this is our B, the damping coefficient, this is our K. So I'm going to write down the forces, because free body diagram is all about the forces acting on the mass. When you isolate the mass from the system, you see how many forces are acting on it. So minus a negative B x dot, and there is another force. If you take a look, this force, which is an input force, it could be an impulse and a step value, a sinusoidal function, or something like this. And then you have to, after you do this, you apply the second law, Newton's second law, mx double dot. If you remember my quiz, I gave the question, the last question was about the derivation of equation of motions. This is similar to that one. So there are three forces acting on it. So I would start from negative bx dot, negative kx, and then positive f of t. Why positive? Because this force is in the same direction as that of the mass displacement. That's why it is positive sign. You should keep the sign convention inconsistent with the convention or with a coordinate. So all these forces are three forces acting on this mass. On the right hand side, this is the kinetics, like where is the mass moving. After you do this, you just rearrange this equation. Second order will come first order will come next, and then zeroth order, which is kx, comes first. So I would write this down. So this is known as the equation of motion of this mass spring damper system. And after that, how will you find out the transfer function? As the definition says, that definition states that Laplace transform of the output over Laplace transform of the input at zero initial conditions. So let's see. So I'm going to find out, this is my output and this is my input. This is my input and this is my output in time domain, but we have to convert this into Laplace domain. So let's find it out. So first of all, I will take the Laplace transform of this whole equation. Laplace transform. I assume that you know the knowledge about how to take the Laplace transform of a differential equation. I assume this because the co-requisite or prerequisite of this lab is control theory class, where you learn this Laplace transform in detail. So let me explain you a little bit. So Laplace transform of x double dot, assuming the initial conditions are 0, is s square x of s. So this will go here, and Laplace transform of x dot. So remember, initial conditions are assumed to be 0 for the otherwise there is another term minus s x of 0 minus x dot 0, but I'm not writing down because the initial conditions are 0, so I'm not writing down these terms. I don't want to confuse you further. So s x of s, and another general term is x of 0. So I'm not writing down this term, so let me write it down here. This is 0. So I can write this down here. This is x of 0 minus x dot of 0. So this goes to 0 because initial conditions are 0. Velocity is 0, displacement is 0. So now Laplace transform of the displacement. What is the Laplace transform of displacement? This is big X. The convention is that the big letters are in the Laplace domain, which is the frequency domain. Small letters are in the time domain, which is small letters. So f of t, the Laplace transform of f of t is f of s. So now we are in a good shape. Now let's plug it in this equation number 1. So let's plug it in. Let me bring this equation down. Okay, So now I will just plug it in the Laplace transforms of all these second order, first order, and zeroth order in the equation. So ms square big X bs big X of s is k big X. And remember, big X, what is big X? This is the output, and the Laplace transform definition says output comes in the numerator, denominator has the input. So let's arrange our equation. Take all the x's common, and f of s is this f of s is cross multiplied to the left hand side, so you're left with m s square plus bs plus k. This is the Laplace transform of the mass spring damper system. I hope you understand that. So let's conclude this Laplace transform. Okay, I would like to mention one more thing, that how would you let's assume m, for example, let's find out the time response. M is 2 kg and b is suppose 2 Newton meter per second, and k is suppose it is 400 Newton per meter, and the driving force is delta, which is maybe like 2. It's okay. Remember the delta, the Laplace transform of, as I mentioned earlier, if you remember, the Laplace transform of impulse is for a unit impulse. This is unit impulse. It is 1. For Laplace transform of a magnitude of 2, you just write down 2, and so on. So in this case, this is a unit impulse, so this is equal to 1. So let me write it down. So what you will do, x of s is equal to 1 over 2s squared plus 2s plus 400 times delta, actually I should write Laplace transform times Laplace transform of delta t. Alright, so now how would you go from this to the time response? This is another technique. You have to take the inverse Laplace transform. So Laplace transform of this one is 1. So let me write down. How would you go from this, let's take this common, to this? What is this? This is by taking the inverse Laplace transform. And I assume that you know how to take the inverse Laplace transform. If you don't know, I have made another video which I would like to share with you, how to take the inverse Laplace transform of different cases. There are 3 cases when you have quadratic roots in the denominator, like in this case, complex roots, then how would you find out? And if you have discrete roots, how would you find out? So I'll share it with you later on.